Hello everybody, welcome to our latest webinar. I'm Martin Carl, I'm the editor of Automotive World, and I'll be moderating today's session, which is entitled Assessing Augmented Reality Content with Virtual Reality. To talk us through this topic, I'm pleased to be joined by experts from Electrobit and Optis, namely Dirk Spieswinkel and Ludovic Menillier. I'll give you a little bit of background to the topic. To design and develop an augmented reality head-up display, or AR-HUD, it's important to take into account a number of crucial factors, including optics and human vision. As we're going to hear, a growing number of factors require prototyping and testing, but of course physical prototyping of emerging technologies requires expensive vehicle customization and, naturally, a physical prototype of the product. Over the next hour, Dirk Spieswinkel, who's product manager at Electrobit, and Ludovic Menillier, who is HUD manager at Optis, are going to outline how virtual prototyping and testing can be leveraged to solve these challenges. We'll hear about augmented reality, the AR-HUD, and how to create, virtually assess, and test an AR-HUD prototype in real-life driving conditions. The format is simple. It's a half-hour or so presentation followed by a Q&A session. If you'd like to ask a question during the Q&A session, please type it into the Q&A box on your screen and we'll address as many relevant questions as possible in the time that we have available. And slides and a recording of the event will be made available afterwards, and we'll send you an email to let you know how and when you can access those. So, assessing augmented reality content with virtual reality. Dirk, Ludovic, over to you.
My name is Dirk Spieswinkel from Electrobit. I'm product manager for in-vehicle augmented reality solutions, and today we will talk about HUDs, HUD design, virtual reality, augmented reality, closed-loop simulation, driver-in-the-loop simulation, and yeah, all very exciting topics. And as this is a joint webinar together with Optis, I will briefly introduce Electrobit. So, about Electrobit, we are a software provider for automotive software and software only. Means we don't do any hardware. We have around about 2,200 employees worldwide, consistent growth over the last years. Our headquarters is located in Germany, near Erlangen, and we have several more branch offices which are located in 3 continents and 10 different countries all over the world. We are owned by Continental, but are an independent subsidiary, and our software solutions are already on the street in over 90 million vehicles and over 1 billion embedded devices. And our core competencies are automotive software products and services. And we serve all current trends of the automotive industry, which means we take care about automated driving, autonomous driving, vehicle infrastructure, connected car user experience, consulting services, and verification and validation. Today's focus will be one part which usually belongs to automated driving. This is the sensor data fusion. So we will hear something about how sensor data can be fused, how it can be made more reliable, more accurate, and we talk about a very exciting thing, user experience, namely a new modality, augmented reality, which is not so common until now in the years. And yeah, that's what Electrobit focuses on, and my colleague Ludovic Menillier from ANSYS OPTIS maybe can give you a short introduction also on ANSYS and what he is doing.
Okay, thank you, Dirk. So I'm Ludovic Menillier. I'm the manager for the ANSYS OPTIS HUD solution. ANSYS OPTIS is also a software editor specialized in light simulation and human vision, used today by 2,500 customers. We are about 250 employees today with 4 R&D centers in Europe. And we have a local presence close to the main automotive development center in Europe, in Asia, and North America. Our solutions are now installed in about 10 VR centers. Optis have recently been acquired by ANSYS, the leader in engineering simulation, offering simulation solution in the field of solid mechanics, thermodynamics, fluid dynamics, and electromagnetics, and now extended with optics. Next slide, please. Yeah. So the story of OPTIS started about 30 years ago with optics and lighting simulation, which is really the DNA of the company. In the early 2000s, the company has been integrated in the technology has been integrated in the major CAD platforms, making it easily accessible for engineers all along the product development process. And then, thanks to a disruptive innovation calculating the spectral luminance, OPTIS provided physics-based rendering capability to support decision-making for product visual appearance. And then we completed with a physiological model of the human eyes. So visual perception simulation was achieved. The light simulation technology was migrated from CPU to GPU, enabling real-time calculation, making it compatible with virtual reality and with simulator. And then more recently, about 3 years ago, thanks to an acquisition, the light perception analysis have been extended to also sound perception analysis. And 3D sound was added also to the VR platform to enable both visual and sound experience. And then finally, as said before, OPTIS joined the ANSYS group, adding adding optics as a new physics to the ANSYS solution, and also mainly to enable the autonomous vehicle virtual testing. Yeah, Dirk, here is for a short introduction of OPTIS.
Yeah, thanks, Ludwig, for this short overview of what OPTIS is doing. And now let me set the frame for you. What is the OPTIS EB partnership about? So we established our partnership earlier this year in April to work together on a co-simulation for virtual testing on augmented reality head-up displays. So you might ask yourself, why do we need virtual testing here? You can test most of traditional HUDs rather easily. You simulate the input, check the output, and you can see it. But unlike traditional user interfaces, an augmented reality user interface cannot be tested at the desk with a straightforward approach. So there is no simple replay of a REST-based simulation possible and compare the output, but this is about simulating the whole environment. So simulating the input for an augmented reality user interface means you would need to simulate the whole environment around the car with a very high accuracy. And also this augmented reality user interface is dynamic, so it changes according to the events which usually happen in the real world. So this is where a special simulation environment is needed, and this is where we employ the OPTIS ANSYS expertise. What is the benefit of a co-simulation here? So we aim to provide a unique commercial off-the-shelf solution that can be used by car makers or tier ones to develop and assess both sensor capabilities and the augmented reality content. And to give everybody a real feeling about how this new exciting user interface behaves, from UX and UI designer to the system engineer who integrates it to the software developer, also to project and product managers and other decision makers. We try to provide something which makes it possible for them to assess this UI. And yeah, we aim to do so in a lifelike driving experience. So having something like a cave simulation where you can directly look and feel how such an augmented reality head-up display might be to the driver. So, Ludovic, maybe you can tell the audience which role virtual reality plays in this co-simulation.
Yeah, thank you for the introduction of the partnership. Yeah, from our side, the augmented reality head-up display as a new paradigm for automotive human-machine interface requires a lot of testing efforts for several aspects, such as the validation of the image requirements from the driver perspective according to the targeted use cases, the navigation, the lane departure warning, the adaptive cruise control, and so on. Also, the human factor studies to ensure the safety and to prevent the risk of distraction during the driving tasks. The verification of embedded software, processing data from the sensor and generating the image at the right position with the right content. And so, thanks to virtual reality, the virtual testing with the software or hardware in the loop can be extended to driver in the loop now with simulation to study drivers' behavior in driving scenarios. And that's the purpose of this collaboration between Electrobit and ANSYS OPTIS, whose basics and objectives are going to be introduced more in detail after.
Yes, so this is the virtual reality part, but of course, virtual reality, that's only in the lab. So how do you do in the real world, enrich the real world with computer-generated graphics? What do you need to do to enable this augmented reality? Because that's the part which is later on the visible thing for the user. So to do augmented reality, you first need to sense your environment. So you need to know how does the real world, which you can see with your own eyes, look like. So you need to sense this using the sensors from within the car, and then you need to create a virtual model of the reality, and that's commonly referred to as an environment model. And with this model, you then can do decisions where and how you want to enrich the reality, where you want to visualize something, and you visualize it in the line of sight so that the driver actually can see it. And there's two different kinds of augmented reality which you can differentiate. One is called live direct augmentation. This means everything where you have a see-through effect, so augmented reality goggles or the windshield and employing an HUD. This is live direct because you see directly the environment, and the other one is the live indirect, where you just have a video feed from the reality and you overlay it with graphics which you generate. And the live direct, that's a bit more demanding. There you have to take care about that all delays in the processing change are very short, so that the computer-generated graphics perfectly overlay. Like you can see in this image, that's on the left side, it's the lane departure warning, and shows you, okay, you need to keep to the middle of the lane to stay safe. But now, Ludo, maybe you can tell us, why would we even need augmented reality in the car?
Yeah. Actually, there are many challenges that are induced by the development of autonomous vehicles. A major one is due to the lack of confidence the consumer have in the system of the vehicle for the moment. Polls clearly show that consumers are still quite reluctant to hand over the control to the system. For example, this study from NerdWallet stated that 3 people over 4 would not put a child in a driverless car, and about 1 over 2 don't think driverless car will be safe. And recently, on behalf of ANSYS, the Society of Automotive Engineers, the SAE, conducted a survey that to gather data on the current and future states of autonomous vehicle development. And the report highlights that the main barrier to the widespread adoption of fully autonomous vehicle is the public confidence and adoption. So build the trust, the confidence in autonomous vehicle must be a priority for the automotive industry to enable large-scale adoption. Next slide, please. Thank you. And for that, head-up display, and especially augmented reality head-up display, will be a good solution to facilitate the adoption, especially during the phase when for level 3 and level 4 will be introduced. The trust can be built by visually highlighting to the driver what the system of his own or her own car detects in the surrounding environment. So beyond the interest for level 3, it will be really essential for the driver. We'll have to take over in a very short delay for the takeover. So thanks to augmented reality, the system can very quickly bring to the attention of the driver where the danger is. So that's for us the main challenge regarding automotive augmented reality.
Okay, so since
maybe
we aim for since we aim for creating an off-the-shelf software solution for co-simulation, let me show you how this augmented reality content could look like in a car and what we currently can produce with our solution here at the Electrobit. So what you can see in this video, this is imagery recorded with a dash cam from our test vehicle here at the Electrobit. We're driving down a highway, and we are employing the sensors which are present already in the car, which is an ADAS camera and which is a radar. We are sensing, okay, where is the lane markings? So the camera recognizes the lane markings, and we use this information in combination with the radar information to highlight here in green. What you can see, we highlight the lane markings, and we are also highlighting the car, so the truck in front of us, which means the adaptive cruise control system, it's following that car. And as you might have seen on the right side here, there was a lane departure warning. Our car was driving too much to the right, and this is the visual feedback you can get combined to the rattling of your steering wheel, which tells you, okay, I need to stay more to the middle of the lane. So that's what we currently can do with our software stack for augmented reality. We are not doing any image processing here, but we let the sensors which are already present in the car, which are already fed with power and which already do the image recognition, we really use that kind of information to enable the display of augmented reality graphics. So let me show you how the software architecture of such a software module looks like. This is the block diagram of our software solution. It's called EB-ARware, and it's split into 3 building blocks. On the left side, you can see your sensor array. So you have different sensors in here in your car. You have an ADAS camera, you have a radar, you have a gyroscope, odometer, which measures the wheel ticks. You have an accelerometer, which tells you, okay, how fast am I accelerating? And you have GPS, possibly other additional sensors which tell you all something about the environment around you. So that's the eyes of the vehicle. And in the middle, we have a data fusion block. Why do we have a data fusion block? For each individual sensor, the information provided might not be ideal or accurate. So you only get a small part of the information from a single sensor. But if you combine this information, you can increase the accuracy and you can increase the reliability of this information. So, and on the right side, we have the visualization. So we have a tooling in which we can create this augmented reality HMI for a head-up display, which is on the bottom right side. So that's the building blocks. I already talked about the sensors. In the data fusion part, we do a lane fusion, which means we can combine lane information recognized by an ADAS camera, and we take additional information from an electronic horizon, which is fed by either a navigation solution or a certain cloud service, and which tells you something about the road ahead of you. And we use that to increase the reliability and the information density of the lane information we have. So we need to know exactly where is the lane in front of me to be able to augment there. Then we have an object fusion part where we combine camera and radar information. That's pre-processed data from the sensors. So we're not doing any computer vision here. We are fusing object lists mainly. And the most important part of this data fusion step is the positioning. So we need a very precise information about the position of the own vehicle and also the orientation. Because as you can imagine, if you are driving over some bumps, this changes the point where you're looking to quite drastically. And if you want to have a good augmented reality solution, you need to show the graphics really at the right place, and this is where the driver actually sees the remote objects. Of course, all those processing doesn't come for free, so there is some latency introduced by processing within the sensors themselves, the transmission of the information, and of course also in the processing part which is responsible to generate the augmented reality graphics. That's why in this data fusion block there is a component called prediction. This one deals with the fact that you need to estimate where exactly do I need the AR graphic at the point in time when it's actually shown on the head-up display. This is a bit a unique thing for head-up displays or for live direct augmentation. You need to have short latencies and you need to ensure the time span is very short, so that you have a very accurate position of the AR graphic. For video augmentation, this is a bit relaxed. You can always delay the video frame a bit and to deal with those latencies, but for head-up displays, that's not the case. On the right side, the visualization stage, we are employing EB-Guide. That's our electrobit tooling for creating automotive user interfaces, commonly used for center stacks or cluster instruments. But we can also leverage it for more complex 3D graphics, and we especially can use it to as a model-driven approach to define the augmented reality user interface. So here's an example. We have different use cases, different workflows. Here we have a lane departure warning workflow, as you saw in the video before with the right arrows. and with the red arrows on the right side, we have this adaptive cruise control where you saw the highlighted arc. What the video didn't show is a navigation use case. You of course could also think, okay, let's visualize to the driver where does he need to go to eliminate the problem with left and right, where people don't know, okay, turn right and then turn left. We can do a visual, an arrow on the road to help and to guide. And of course, a 3D rendering part to get this all drawn and then send up to the head-up display. So in this diagram, there's basically two hardware blocks on it. That's the sensor part and the head-up display part. One is the input for our software solution, and the other one is the output sync. And yeah, that's what you also need to take care of if you want to provide a complete simulation of this whole augmented reality head-up display driver use case. Let's put it like this. And yeah, Ludo, please tell us what can ANSYS do to work on simulating those sensor and head-up display parts?
Yeah, to help the car makers and the supply chain to develop augmented reality head-up display, the ANSYS OPTIS HUD solution rely on two fundamentals. First, a virtual reality environment, because it places the user, the driver, at the heart of the HUD visual experience. And so based on our VR platform, it displays in real time the HUD virtual image in immersive environment with stereo display and tracking system. And this both for the early stage of the process to specify the ideal HUD virtual image, characteristic, and content. And then later, at the later stage, to intuitively assess the perceived quality of the virtual image produced by an actual HUD optical system. And then, in parallel to the VR environment, we have a CAD integrated set of tools because the CAD and the PLM is really the key platform for all the detailed engineering and the collaboration between OEM departments and the suppliers. So we find here features to design the PGU, for example, assess the lighting performances, such as the luminance, the uniformity, the colors, and also features to design the imaging optical system, and then to validate the image quality against the requirement from the car maker. Next slide, please. Yeah. So let's now review some more in detail some of the use cases addressed by the VRXPERIENCE platform. Some of them are under development, and some are already in production. This is the case for the development of the glare-free headlight systems, such as the matrix beam or the pixel beam, which come as a natural extension of our legacy solution, ANSYS VRXPERIENCE, for the headlamp optical design. So the key capability we propose here with the platform is the co-simulation between driving simulation with traffic to get the road 3D scene and driving scenario with incoming and preceding vehicles and even pedestrians, and also the real-time lighting simulation, calculating the illumination on the road and the driving scene from the headlamp, detailed optical design, and the materials with their optical properties applied on the scene geometry. And finally, co-simulation with the headlamp control law, switching off or on some area of the light beam, as illustrated on the left side. Let's now see the recording of such co-simulation. We can see a typical driving scenario on the countryside road in night condition, of course. The scene is illuminated by the headlights of both the Ego car and other cars. We have also both incoming and preceding cars, and the sensor detects the location and the size of the other car, which allow the system to control the MEMS matrix of the lamp, and so avoiding to create glare for the other road users. Okay, so that's for the headlamp use case. We can switch to the next one, which is the sensor. We are developing now this use case to address optical sensors integration challenges. So both camera and LIDAR sensor are available for early adopter, which want to develop smart sensors data processing. So before the capability being released for car makers and suppliers. So with December release for cameras and mid next year for LIDAR. The key capability here is to simulate in real time the raw signal generated by optical sensor. So for both sensor types, a physical model has been developed. It includes the optical lens, the receiver, and for the LIDAR, the emitter, as it is an active sensor. Of course, to get reliable sensor simulated signals, an accurate lighting simulation of the environment is mandatory, is essential. So you can see on the video that have been created with a partner, LIDAR Tech, a company developing the next generation of LIDAR around its dedicated integrated circuit technology. The scenario here is a two-wheeler passing over a vehicle which changed its lane due to some construction, and you can see on the on the right side of the road, a camera and a low-resolution LIDAR have been installed on the front, and two side high-resolution LIDAR have been installed on the back. So you can see the raw signal in orange of each sensor are simulated, and they can feed in real time data extraction processing provided by the smart sensor, and then thereby enabling full virtual testing. And then we can go to the next one. A third use case we are developing also currently with a car manufacturer as a partner to include the driver this time in the visual experience. The driver in the loop experience is provided by an immersive environment with tracking system and 3D display such as HMD, Powerwall, or Cave. The experience can be enhanced with 3D sound experience. We have finger tracking capability that is going to enable natural interaction with the switches on the touch screen. And the central console display or digital cluster display can display dynamic content and the virtual image content generated in real time by Electrobit software, and is going to be presented to the driver by this way. So thanks to a dedicated feature using as input the standard HUD characteristics such as the projection distance, the field of view, or the look down longer. Okay, we can now have a look on the architecture we are building. So from the platform, the VRXPERIENCE platform side, it includes three main components we introduced previously. So at the heart of it, we have the driving simulator, which provides the driving environment with traffic simulation. and then which is connected to the real-time lighting simulation components coming from our legacy simulation technology, but here implemented on GPU to achieve real-time calculation. And we have also here the physical optical sensor relying on the lighting simulation too, in order to feed the system part with accurate raw signals. And finally, the HMI component fed this time itself by the system parts, which with the HUD image content stream to be presented to the driver during the driving experience. And so maybe, yes, you can explain the side, your side from Electrobit?
Yes, of course I can. On the right side, you can see our augmented reality solution, EB-ARware, and from bottom to up, we utilize the information provided by VRXPERIENCE. So we take the information from the lighting and the sensors. So and first we do a sensor abstraction, because our processing core with the data fusion that is sensor agnostic. So we take the output, abstract from the specific encoding of the individual sensor you maybe have simulated, and then take this information to the data fusion core and enrich and make that information more reliable by using the data fusion steps described before, and then engage in the visualization. And on the end, what we get is those computer-generated AR graphics, and they can be an overlay to the VRXPERIENCE simulation. So you can actually simulate the whole chain. You get a rendered image from the simulator, so you actually see where you're going. Beneath, you have the simulation of your optical sensors, and they are fed back, and you can close the loop. And if you think about what does this enable, you can have a cave simulator, you can sit in it, you can actually steer the steering wheel angle, and you directly can experience in a simulator how it would look like later on the road. And yeah, I think that's a great thing to do, and has a lot of benefits. So what we can do is we can have a look at the first impressions. It's still in an early stage, but yeah, we will get it covered pretty soon. So what you can see here is you can see the images rendered from the VRXPERIENCE, so the virtual reality. And what you can see on the bottom is already graphics rendered by EB-ARware. So we have closed the loop. This is more like a traditional 2D head-up display element, but we just started closing the loop, so we are still on the sensor abstraction part. It is, as explained earlier, it's rather difficult to do this as a simulation and to have all those sensor signals in a way like they would be in a real car, because it's highly asynchronous, so every sensor runs on its own, and you really need to see, do I match all criteria which are really present in a car on the road. So there's still some work to do on the simulation part and on the processing part of the sensor information, but the first step is done, so we can actually calculate a position. Right now we're working on the object positions and the lane information, but I'm already excited how it will look like once we have also the possibility to highlight the other cars and to implement all our ideas which we have regarding augmented reality workflows. So overall, what would be in it for you with such a joint solution, such a closed loop solution? You would be able to improve the quality a lot, because this simulation will give you insights into the underlying physics. So this applies to HUD and sensor design and the system architecture, and you would be able to directly spot if you're heading the wrong way here. And another plus point would be you can be really fast to the market. So you could simulate everything and do the physical prototyping and testing later. It enables a very quick feedback loop. With our HMI tooling, EB Guide, you, for example, can directly change the coloring, the size of augmented reality graphic elements, like this adaptive cruise control highlighting we've seen in the first video. If you don't like it in orange, rather would have it in blue or red, or want to assess how does it feel for the driver if it's in a different color, this can be done very easily. You don't need to leave the lab and drive with the car. You can do it in a cave simulation directly. And by that, of course, you can save a lot of money. It's far less expensive than physical prototyping and testing. And yeah, I'm excited once we have it done, how it really feels and looks. And yeah, that's how you actually can assess augmented reality content with virtual reality and in a simulation. And if you have any questions, please feel free to ask now, or also later mail to Automotive Megatrends, and they will hand over the questions to Ludovic and me, and we can answer them for you, hopefully. Thanks.
Excellent. Thank you very much, Dirk and Ludovic, for sharing your insight with us. As we have already said, if you would like to ask a question now, please type it into the Q&A box. We'll put as many relevant questions as possible to Dirk and Ludovic over the next few minutes that remain of this hour-long session. We've had quite a few questions come in already. I wonder if I'll try and put these to you in some kind of order, but there's a wide variety of topics already being addressed to us. So perhaps you can talk a little bit about how what technologies are being used now, and what improvements in the technology you would like to see that might help improve your processes. Is there anything specific where you're hoping that a certain sensor can be improved over the next year or few years that would enable you to significantly advance what you're doing?
Well, it depends what kind of aspect we are talking about. So if we're talking about getting a very smooth augmented reality experience where we have a perfect registration between the generated graphics and the reality, I would hope that inertial sensors might get a bit cheaper and have an increased accuracy. That's one part, but of course also from a camera perspective, we are more moving towards a centralized architecture where the processing of the raw sensor data is done maybe on a high-performance computer. That would enable us to generate a more accurate environment model. So getting, for example, delta values from the visual flux would be a really good thing. So we could estimate the orientation of the vehicle much better, and by that improve the augmented reality experience. And of course, looking forward to see LIDARs in cars, this would also give more possibilities for use cases.
Okay, thank you. What kind of AR-HUD use cases can you prototype?
Yeah, first of all, you can prototype those I mentioned already. So you can do a variety of navigation use cases, like have different visualizations for different type of roads, and you can say, okay, let's do the roundabout different than the highway exit or exit ramps in certain ways. Of course, you can bring in information from a navigation solution, like in addition show where pure eyes are, if there's anything important, anything interesting to the driver. This is information you can use to enrich what you're just seeing with your eyes already.
All right, thank you. I think this one might be best for Ludovic. How would you simulate eye adaptation to light and the driver's age, for example, recreating the exact vision of actual drivers for the most accurate results?
The way the eye reacts to the ambient light can be modeled thanks to the calculation of the distribution of luminance, which is the matrix, the photometric matrix that is sensitive to the eye is sensitive to. So that's thanks to the calculation of the luminance, the spectral luminance that we can't feed the human eye model. It's something that we have implemented maybe 20 years ago now in offline simulation, and that's something we started to implement it in real time. And for instance, the effect of the ambient light, the global ambient light, and then we can adjust that according to the model to the age of the driver. Also, thanks to that, we can simulate the glare effect. So what happens in the eye. So basically, the key capability we have behind that is the ability to model and to simulate, to calculate the luminance distribution. So that does require a physical model of the scene, not just, I would say, a visualization part.
Okay, Dirk, during your previous answer, you mentioned about the whole process being smoother. There, we're talking about the actual technology being smoother. But how would you how would you deal with driver movement in a driving scenario with AR-HUD?
Yes, there's two different aspects to driver movement. Maybe if you also mean by how do you detect a small or large driver, so having this aspect in the vertical axis, this can be done like with normal HUDs, where you just have move the actual mirror a bit, and by that adjust it. So this could be done by using an interior camera which sees the driver and says, okay, this is a small person or a tall person. And when it comes to movement of the head in maybe a horizontal direction, as long as the driver doesn't move his head out of the eye box, where you would see the HUD graphic to be cut anyway, because of physics, you just cannot move outside of it, because the area available to the projector itself is limited. But as long as you are within those bounds, the effect of the driver's head movement is not so large after all. But this is specific to the head-up display employed and to the projection distance of the virtual image. Yeah, this has to do with the parallax effect. So if the virtual image is far away, the angle actually is rather small. And if you use a real augmented reality head-up display, like those which are currently still in development and which did not hit the market yet, and they typically have a projection distance of 7.5 meters upwards, and the driver head's movement is not so important for those. Of course, if the image is closer, maybe only 4 meters or 3 meters, the parallax effect is larger, and one could think about using an interior camera to maybe reduce this effect. But yeah, if you employ such an HUD with a shorter projection distance, you have other drawbacks, like the eye needs to refocus on the AR graphics because they are appearing to be too close, which is somehow, yeah, it drains the full experience of augmented reality. So recommendation would be use an augmented reality head-up display with a projection distance of 7.5 meters onwards, and you are safe for most of the driver's head movement.
Okay, thank you. We've had a variety of questions. I'm just trying to select the ones that might draw in as much information as possible. One of the questions that struck me from an audience member here is how, whilst the system seems interesting, it also seems very complex to manage. Can you talk a little bit about how the engineers might understand what processes they need to go through, how you might be able to sell this technology to a customer, and in order that they make the most out of the products and the solutions that they can get from this?
Yeah, I think the crucial part when designing an augmented reality head-up display system as a whole, so both the head-up display projector itself plus the software you need to generate the augmented reality graphics. The crucial part is estimating the vehicle movement and the vehicle orientation, and for that you will need a lot of insight on the dynamics of the vehicle. So you need a precise model of the dynamics to get the estimates right. That's a crucial part, and with this co-simulation you can do this somehow upfront. You can benchmark your algorithms. You can check, okay, is my sensor really smart enough? Is it good enough to really provide the input which is required for good augmented reality experience? And yeah, that's one of the benefits of this whole simulation thing. You are closed loop. You can bring in hardware. You can bring in the software from your sensor and really see directly in the lab, is this good enough already, or do we still need to tweak something?
Okay, we've had a couple of questions specific to the software itself. I don't know how much information you can give us, but we've had a few questions asking what software is used for augmenting data, and also what SDK do you use?
Yeah, well, the software we use is Electrobit arware. That's our product we sell for creating augmented reality graphics in the car. And yeah, there is no direct underlying SDK apart from the visualization part, where we reuse the EB guide toolchain, HMI toolchain, but all this sensor fusion and position estimation, orientation estimated, that's built into EB arware.
All right, and here's an interesting question that's come in. Have you studied the perceptual differences between AR and VR? And if you have, can you tell us a little bit about that? Bearing in mind that we're very close to the end of our hour session, but if you can get an answer along those lines in, that'd be great.
I think, Ludo, this one is for you. So.
Yeah, I'm not sure to clearly understand the question, but augmented reality, one of the differences is the fact that the image is projected at the long distance. So then we do not have accommodation to do between the exterior scene and the augmentation. So that's one of the benefits in terms of visual comfort. In case of short distance display on the windshield, for example, then you would have to adapt on a short distance and that creates the same kind of effect you may have with a standard like the cluster, I would say.
Okay, thank you. Well, I think we've come to a perfect conclusion there for this webinar. Thank you very much, Dirk and Ludovic, for sharing your insight with us, and to EB and OPTIS for making this webinar possible. As I said before, there will be an opportunity to download slides and a recording of this webinar. We'll send you an email to let you know how and when you can access those. And with that, I'd like to draw the session to a close. Thanks everybody for tuning in, and we'll see you at the next webinar. Thanks very much, and goodbye.